So this talk is entitled Applications of EMCCDs to Faint Occultations. And it's really an extension of a talk that Steve Conard presented last year at the IOTA meeting, where he looked at the signal-to-noise ratio of typical IOTA cameras such as the Super Circuits, TC164 CEX2, the Wadtec 902 Ultimate, and the Stellacam EX. Today we'll look at some rather remarkable higher-end cameras that use electron multiplying on the CCD chip itself, and I'll be abbreviating them EMCCDs, and we'll be looking at how they may be useful for faint occultations. So the next slide. The agenda, first we'll talk about what we may consider to be faint, what and how EMCCDs operate, some signal-to-noise ratio theory and tests in the field, and some projects to extend the usefulness of EMCCDs. Next slide. So for this talk, what is considered faint is a desirable occultation out of the reach of typical IOTA equipment. And this could be where the targets are faint, for example, TNO occultations where the objects are 14th magnitude and fainter, where a particularly fast cadence or what we would call high time resolution astronomy project is underway. For example, observing diffraction patterns where we may want to operate at 200 frames per second or faster, where small scopes are in use, primarily for portability, and typically they're well under 1 meter, or in lowland observing sites, or when the program object is at a low altitude and there's lots of atmospheric extinction. So the next slide, please. So EMCCDs, as I previously said, employ electron multiplying through an extra set of registers. In a minute, we'll look at how that works. But just to get an idea of some of the types of cameras that are available on the market, the picture on the lower left has 4 EMCCD cameras. The 3 large silver cameras are photometrics cascade type EMCCD cameras. And the camera on the lower left of that picture that looks like a part of a Wankel rotary engine is a Luca S, an indoor Luca S EMCCD camera. On the right-hand picture, we have 3 indoor eyes-on EM cameras, which are really the top of the line indoor EM cameras, EMCCD cameras that are available. Next slide, please. So how EMCCDs work, first on the left side of this picture is how a traditional CCD readout works. The pixels are clocked out to some registers which are processed serially out to a readout amplifier. With an EMCCD type camera, we really get the best of both worlds. You have the traditional type of amplifier, and you can see this on the right-hand part of the picture where the readout would happen in a normal fashion using normal clock voltages, But you have this other set of special registers where when the photoelectrons are clocked from one register to another, a higher voltage is used, and each time the charge is clocked to a neighboring register, there's a small percentage chance that an impact electron will be released. And after hundreds of clock cycles, the net result is that the compounding of that small probability becomes a overall gain of hundreds to 1,000 or so. Next slide. So really what these two slides show, in particular the one on the left, which I'll talk about now, illustrates what happens to the CCD readout noise as the EM gain is increased. When the gain is very low, as seen on the x-axis, the readout noise on the y-axis is comparable to what a traditional CCD chip would produce, on the order of 10 or more electrons. And as the gain is increased, the readout noise winds up decreasing, because one photoelectron will produce hundreds or thousands of electrons that the amplifier needs to process. And the readout noise drops dramatically to 100th or more of what it was normally. In addition, these higher end cameras from Andor and Photometrics are often, well, in this case, use very capable CCD chips, and the top curve of the graph on the right shows the quantum efficiency as a function of wavelength for the Photometrics and Andor top-end cameras that we saw in that picture of the cameras, peaking quantum efficiency of over 90%, and the lower curves are the quantum efficiency of the typical type of IOTA camera, the bottom two curves. And in particular, out towards the longer wavelengths, the quantum efficiency of the cameras is several times greater than the quantum efficiency of the typical IOTA camera. Okay, please turn to the next slide. This chart here displays some camera specifications. A couple of the typical IOTA cameras are on the top two rows, and the EMCCD cameras that we're really talking about today are on the bottom two rows. What's typical of the EMCCD cameras are that the pixel size tends to be larger than the typical IOTA camera. The pixel well depth winds up being much larger as well. Instead of 8, 10, or 12 bits, it's 14 or 16 bits. And the price is orders of magnitude greater. Although I've purchased over 10 EMCCD cameras, and a large number of them came from eBay. And on eBay, one can find the Photometrics EMCCD cameras from between about $1,500 and $5,000, and sometimes one can find a good deal on the Andor ones as well. And in my case, those 3 Andor eyes-on EMCCD cameras I bought from somebody on eBay He was advertising one of them. I asked him if he had any others, and made a deal for all three. The next slide. So you're probably wondering, how would we mount a big camera like that on a small scope? And here are some pictures showing just that. The top two pictures are the Photometrics Cascade 512B mounted on a 10-inch SCT. The photo to the immediate right of the lettering on the slide is a Luca S on the back of an 8-inch SCT, and the one to the far right is the Photometrics 512B mounted on a 10-inch Newtonian. The next slide, please. And this slide is a picture of the optical head at Russ Genet's observatory. It's a 10-inch SCT with an Andor Luca S. He has an Orion filter wheel, a 2X Barlow. The finder is not an eyes-on right at this moment here. It's actually in the picture an SBIG ST402, I believe. And he has a Van Slikey, or I believe that's how you pronounce it, instrument slider. And this is set up for speckle interferometry, where he's observing hundreds of frames per second. Next slide. There was a question that had come up from Tony, are we using focal reducers? With the large pixels on the EMCCDs that we use, which are typically 3 times larger than the pixel size on the typical IOTA camera, we really haven't needed to use focal reducers, and we're able to concentrate the stellar light onto just a few pixels. Okay, so this next slide is of this signal-to-noise ratio theory for a 14-inch SCT, and I was when generating this graph here, trying to model Steve Conard's observatory. The graph along the x-axis shows the apparent brightness of the program object, and along the y-axis the signal-to-noise ratio. And this is at video rates, 30 frames per second. Predicted performance, taking into account scintillation, shot noise, read noise, and other noise sources, scintillation and extinction. What we have is 4 cameras graphed. The green curve is a Super Circuits 164 CEX2. The blue curve is an Andor Luca S. The red curve is a Luminera Sky NYX 2-0. And the purple curve is a Photometrics 512B. This is predicted performance. What one sees is at the brighter end, towards the left in the graph, all of the cameras converge and are limited in their signal-to-noise ratio by scintillation, and it won't matter how good your camera is, you're limited in that region. Towards the right, however, as we move towards fainter objects, the signal-to-noise ratio attainable with the typical IOTA camera falls off with this size telescope at around 12 or 12.5 magnitude, and this is again at 30 frames per second, versus the EMCCD camera, which will yield about the same signal-to-noise ratio, 2 to 3 magnitudes fainter. And the Photometrics Cascade 512B gives a little bit better performance than the Luca S, primarily because that's a back illuminated camera and the Andor is front illuminated. For each magnitude fainter worked, you're picking up about 300% more targets. So 2.5 magnitudes is about 30 times more possible occultation targets. So this is a very significant technology in theory. So let's see how it works in practice. The next slide, please. We were attempting to observe some, or hoping to observe some TNO occultations with our cameras, and haven't had the luck, although we've tried on some 16th, 17th, and I think Steve set up for an 18th magnitude occultation. But what Steve did at his observatory using one of our Photometrics Cascade 512Bs is observe the cluster NGC 7031, where the stars were ID'd down to around the 17th magnitude. The first check was really just linearity. Last year, Steve had reported on the typical IOTA cameras and found that his Stellacam EX had similar performance to the Super Circuit 164. So the left-hand curve here, checking linearity, and also the right-hand curve for the photometrics. Both cameras appear to be very linear with regards to the expected output based on the known magnitudes of the stars in the cluster. The next slide, please. So this next slide shows the signal-to-noise ratio. On the left, again, we have the Stellacam EX, and just like the theory had predicted, the signal-to-noise ratio falls off around 12.5 magnitude, and when one uses the EMCCD, everything else being the same. It wasn't the same night, but the object was the same position in the sky. With the Photometrics 512B, the cluster members that were able to be observed above, say, magnitude or signal-to-noise ratio 4 extended out to around 15th magnitude. So it was confirming what our expectation was, that with everything else being equal, the EMCCD cameras are able to work 2 to 3 magnitudes fainter than the traditional type of camera. Next slide, please. Some lunar occultations that we have observed with the EMCCD cameras include mu-gem. We observed this with a C8, the Luca S. We ran it at 333 frames per second. And the mu-gem is a very large apparent size star, around 16 milliarcseconds. And the upper left graph is the data with the red curve being a 16.5 milliarcsecond fit. And it really didn't fit that well, and we were thinking, well, maybe we're seeing some kind of spotting or something, so we fit it with a much smaller apparent diameter object, and it fit much better. But then when one looks at the real extended data set, one sees that it's just it's just noise. Now there's a question here. Was it the same night within about 15 minutes with the target near zero? It was the same. Sorry, Steve says that that previous slide, it was the same night with about 15 minutes between the measures. And then Terry asked 30 frames per second digital record. Can you frame stamp the time at 300 frames per second? I'll get into that in a minute, Terry. The way the data was recorded was at 30 frames per second in both circumstances. Okay, so back to this mu-gem slide. The scintillation, again, was the limiting factor at being able to do any science with this type of occultation. The scintillation essentially masked any useful science. Next slide. Okay. So this was another occultation, Pi Sagittarii. It was the two graphs were made with two different telescopes, both C8s. They were side by side. The top graph was made with a Super Circuits 164CX2 at 30 frames per second, and the bottom one was made with an Andor Luca S running at 120 frames per second. Again, what we see is that scintillation totally masked any useful science that one may have gotten at the higher frame rate. Dave had said to resolve the Fresnel diffraction patterns, you need to use filtered light, not unfiltered. And to make the diffraction patterns optimal, that's true. But even with monochromatic light, the brightness difference is only 40% at the peak of the diffraction curve, and the scintillation noise was greater than that. It totally destroyed our the science that we were hoping to get on mu-gem. Okay, next slide. So some projects that we have underway to enhance the value of our EMCCD cameras are to get at Terry Redding's question about timing. All of the EMCCD cameras have external timing or pulse triggers, and we are building a programmable timing trigger device based around an Arduino and a GPS shield. It's turning out that the stock Arduino isn't really powerful enough. My son just told me about the new Intel Galileo Arduino, which actually has a Pentium type chip, special chip in it, and that will probably give us the additional performance that we need to trigger these cameras with a high degree of reliability to the microsecond level. Additionally, we have underway some projects as part of the OLTAS telescope initiative to deal with the scintillation problem. These EMCCD cameras have really resolved a lot of the read noise problem, but we're working on building some larger scopes which are portable to further improve the signal to noise ratio. In the picture to the right there is my nephew Charlie. He just put together this Hubble Optics UL20 20-inch aperture telescope. The OTA and mount weigh about 70 pounds and come apart very easily. With the mirror and everything, including the SciTech mount, encoders and motors, the entire telescope is about 105 pounds or so. On the next slide, we have some other, I'll just show you some other larger portable telescope projects underway. This one is a 1 meter meniscus mirror telescope that Russ Genet built. He nicknamed it Big Blue. My son drove it from California back east to Philadelphia area in the back of our minivan. And so it really shows just how portable a 1 meter telescope can be. It's able to be set up in under 30 minutes, and that includes alignment as well. Next slide. Not to be outdone, Russ marshaled considerable resources with his contacts at Cal Poly. A number of students there participated in a project of scaling up Big Blue to 1.5 meters. As you can see in the lower left, it's all CAD designed, CNC machined out of this high-tech plywood. On the picture on the right, about a week and a half ago, it had first light, 60 inches, able to be moved around. I'm not sure what the weight is, but I don't think it's too much more than Big Blue. So it's eminently portable, although it may not be able to be set up in quite as easily as Big Blue in less than 30 minutes. Next slide. And the last project, which is going to be the home for our EMCCDs, is a scaled up from the previous slide version that Russ Genet has been spearheading along with several of us to make the largest size telescope that's transportable down the road in the back of a flatbed truck or tractor trailer. And in fact, in the lower right, we've been doing a lot of simulations, and about an array of about 7 of these scopes would have photometric performance that's comparable to a single 8 meter telescope such as Gemini. And a lot of that performance is due to the ability to deal more effectively with scintillation when the array is spread out. Next slide. So in conclusion, EMCCDs cameras can help IOTA in certain circumstances. They have a couple 2 to 3 magnitude advantage at video rates over typical IOTA cameras on the same telescope, hardware, and observing location. They're good on photon challenged small aperture scopes. They're very useful for low altitude or low contrast events where an ideal signal to, or an optimal signal to noise ratio is needed, or it's just outside the range of what's attainable with the typical IOTA camera. They are challenged in certain circumstances because they're a lot more expensive. They're heavier on the order of 6 or 7 pounds versus several ounces. You need to have a decent mount on your telescope or have it fixed and aimed at a certain point in the sky. They are less portable. If you're trying to take it on an airplane and you have a certain budget of 70 pounds or something like that, it eats into that. And they need more power. We have run them off of batteries, although the type of battery that they need is like a motorcycle battery or a car battery, or better yet, some kind of motorboat deep discharge battery. And in any case, what we've shown, we've expected and we've shown is that scintillation noise hampers our fast cadence and high time resolution measures. So one really needs larger scopes that are half a meter or larger if one is going to try and effectively go after diffraction patterns. At least that's what we expect. So that's the talk. The very last slide just has our contact information on it. Are there any other questions? Okay, I don't know. Oh. Bruce, have you compared EMCCDs to CMOS? We actually did acquire one CMOS camera for science observing, and found that the sensitivity was nowhere near as good as our EMCCD cameras. The other thing about EMCCDs, because they're EMCCDs and they have a single output amplifier, one gets a very linear response pixel to pixel, and scientific CMOS cameras have a separate CMOS amplifier per pixel, and the net result is there is a very wide range of amplification that one gets inherent in the CMOS type architecture. And so careful calibration has to be accomplished with the scientific CMOS cameras to linearize the output, remove bright pixels and other problems like that. Okay. Are there any other questions? Okay, thank you.